Hi, I'm Sam Roberts from Roberts Geospatial Engineering. Today we're going to go hunting for meteorite impact craters in Mauritania in northern Africa. So we're going to be using ProRaster Scientific today. This is software that I develop and that I sell, and it's the reason I make these videos. It comes in 3 tiers: Essential, Premium and Scientific. You can get it from the Microsoft Store. You can get a 7-day free trial, and then after 7 days you can either uninstall or you can purchase the software. If you have an x64, Intel or AMD processor, this software is for you. If you're using an ARM64 processor, that might be an Apple PC or it might be a Copilot Plus PC with a Snapdragon CPU, as of late February 2026, we can't offer you the software. So we're going to be hunting for meteorites using the GLOW 30 DEM. So this comes from the European Space Agency. It's a global terrain model of the Earth at 1 arcsecond resolution, which is about 30 meters or 25 meters on the ground. We're also going to be using some Landsat data. You can get this for free from the USGS. This is their Earth Explorer website, and I just downloaded a few scenes from that website, and we'll look at that in ProRaster Scientific. We're going to start by looking at the Richat structure. You can see it on screen here. We're going to talk about how it formed. Was it the location of Atlantis, as many people who comment on my videos seem to think? Is it a meteorite impact crater? Is it a geological structure? To find out a bit more, you could go to a YouTube video like this by Maria Bias. She has geological videos and she'll tell you about the geology of this structure. We're going to talk not so much about Atlantis, but about another interesting mystery in the Mauritanian desert, and that's the Chinguetti Meteorite. And there's a video on YouTube that you can find about this meteorite that describes an expedition that went searching for it. So we're going to be looking at that, and we're going to do a bit of searching ourselves, and we're going to be looking for and finding some other meteorite craters in Mauritania and comparing them to others around the world. So we're going to start with Google Maps. Mauritania is in North Africa, largely covered by sand dunes and the Sahara Desert. So at this altitude, which I don't know might be something like 10,000 kilometers, the Eye of Africa, the Richat structure, is already actually visible. So in other words, not only can you see this thing from space, you can see this thing when you're on your way to the moon. If we come down to the altitude of, the space station or something like that, perhaps more like this, there's the Eye of Africa, there's the Richat structure, and you'll be able to see it very clearly from that sort of 500 kilometer orbital altitude. So let's start with our global terrain. The Richat structure is in here, and you don't have to zoom in very far before it starts to become visible as a significant circular topographic feature. So this thing really sticks out like dog's balls. And you can see the environment in which it lies. So there's some kind of plain here, and you can see all of these vast dunes from the Sahara Desert, all different kinds of dune fields to the north and to the south. And indeed some even coming across the Richat structure itself. So some people think that this is the location of Atlantis because of the circular nature of it and the way that it was described, the way that Atlantis was described. People originally thought it might have been some kind of meteorite impact crater, but these days people describe it as being a domal anticline, so there's a large magma chamber underneath this structure which has uplifted the geology, and the top has been eroded off and left behind this the skeleton of the rocks underneath, which have this circular expression because of the domal anticline. One little feature that's interesting is you can see there's kind of a little Richat forming over here. I don't know quite what's going on there, but you're seeing a little dome structure there by the looks. So let's have a look at our algorithm. Perhaps put on aerial imagery. And you can see what we're looking at here. This is the Richat Structure. Here are all the sand dunes off to the south. We can't really get much out of that. If I turn on street maps, you can see that almost nothing comes up. There is no infrastructure in this area. There are some towns down here to the southwest. Here's Chinguetti, and we'll come back to that. But basically, this whole area is extremely isolated. There's nothing out there, and on that basis, it's probably very unlikely that there ever was. Although there is some archaeological artifacts around, some carvings and so forth in the rocks. Turn on some contours. So you can see that there's a plain around this structure, and then there's a cliff line, and it drops down into the structure, and then there's various concentric hills within the structure. Now, the interesting thing about this, from my perspective, is how did it form? Okay, we get the story that there was uplift, the top got eroded off, it left this concentric ring structure. But then when you look at it, it's a bit harder to see how the mechanics of that actually worked, bearing in mind that we're talking about a very, very long period of time, possibly 100 million years. So let's come back to our algorithm. And we'll take a look at it in 3D. Oops. So let's just adjust our 3D map settings. You can scale down to about 20. And if you zoom in, you can see the sand dunes to the southwest, and you can see how the structure sits within a plateau that is higher than the structure itself. So the thing is actually eroded out from this plane. Now, what I find difficult to get to terms with is how it got eroded out, when if you look at the topography, all of the streams around it actually flow into the Richat Structure. So if it rains in the Richat Structure today, that water isn't going out, it's going to pool there and just stay there. It probably doesn't rain very often. And so that begs the question, how does a structure like this get eroded in this way if there's no way for the sediments to actually get removed from the area? And I wonder whether the answer is over here. At present, this area is above the level of the Richat Plain, but perhaps in the past it wasn't. You can see that we'll see this a bit more clearly later on when we look at the Landsat data. But there is a set of sand dunes coming through here, and perhaps this valley has been filled in by sand and is now blocking the egress of water from the Richat Structure. Because there is an old river course that comes underneath these sand dunes and flows out to the ocean. So maybe that is how erosion, water-driven erosion actually took place and actually eroded this out from the plain. Let's take a look at the Landsat data. So I'm going to bring in some Landsat scenes directly into ProRaster Scientific. So I've downloaded the scenes and I've unzipped them each into a directory. They are collection 2 level 1 scenes. I like level 1 because you get the panchromatic data band, which you don't get in the level 2 data, even though the level 2 data is corrected to bottom of atmosphere and is theoretically better. I like the level 1 data. So I'm going to add scenes to a new database by folder search. I'm going to name my database. We'll call it Richat. And then I'm just going to browse to my data. So in my multispectral Richat structure. So here's my 4 scenes. They're each in their own folder. We can't see them at the moment, but I'm just going to go to the top of that and go select that folder, and it's going to parse through all those folders and find those scenes, and we now have a new satellite scene database with our 4 scenes in it. And now I'm just going to turn that into a mosaic. So I'll select those 4 scenes. I'm going to create either a mosaic or a composited mosaic. Compositing allows you to overlay scenes and make sure that you get the best data from each scene, taking out clouds and so forth. So I'll create a composited mosaic. I'll make a new product database. So I'll call this Richat. So here are my scenes. I'm not going to change anything. We're going to clip all the cloud out of these scenes, and where we have overlapping scenes, we're going to take the best data, just going to hit OK, and now I'm in my product editor. So I have my composited mosaic. There's my 4 scenes put together into a single product, which I can now work with. So we're not going to do any processing. I'm just going to display it. And I'm going to use the shortwave infrared red, green, blue combination, and I'll turn on pan sharpening. So I'll close my product editor now. So here's the Landsat data. And this starts to really bring out in sharp relief the fact that we have all this sand in the southern part of the structure and through this part here. So let's go back to our 3D. So I'm just going to add in a 3D surface, connect that to my Glow 30 data. There it is, finally. Okay, so looking at this now, I won't bother to adjust the scale, but you can really clearly see all these sand dunes in this southern area, and possibly, imagine that this has all been filled in by sand, and that in the past there was a river flowing out of here and eroding this structure. With the Landsat data, you can begin to see some different coloration in the rocks. So where we have harder geology, igneous rocks and so forth, then we get hills where it doesn't erode as quickly, and you can see some of that as a coloration difference in the multispectral data from Landsat. So coming back to our topography, I've increased the amount of hill shading that we see. Zooming in here on Mauritania. Here's our Richat structure. Let's look now for other meteorite impact craters that are around the place. It's quite rich pickings in Mauritania. So leaving behind the Richat and the little Richat, whatever that is, we just come down here a little bit. You can just start to see something here, and it pops out. And there's a tiny little meteor impact crater. Let's turn on the aerial imagery. Hardly anything to be seen. Push that out to a 3D map. Sorry, my internet's a bit slow to bring down the imagery. So there it is, only a very small little crater. It's called the, hard to pronounce, Aouelloul crater. Aouelloul or something like that. And it's about 400 meters across. But quite definitely a neat little impact crater. Turn that imagery off again. The other one is much easier to spot. Go back up past the Richat Structure, over this sand dune field to the north, and then this one really jumps out at you. Quite a significant crater. Let me get the distance tool onto that. This one is more like 2 kilometers across. Let's get our imagery on. So this time we're getting more of a expression of this thing in the imagery. Push that out to 3. And that one is, quite spectacular. Really sharply defined little meteorite impact crater. That one's called the Tenoumer Crater, I believe. So those two, let me get this on off again, the imagery. Those two really poke out of the ground. There is apparently another one down to the south near the border with Mali called the Goji Crater, but I haven't been able to locate it. I can't find it in the data. So let's just compare those very quickly to some other craters that you might know. So for example, over here in the US, you have Meteor Crater in Arizona. Let's get a distance on that. So this one's about 1.2 kilometers across by about 1.1 kilometers in the other dimension. So the Tenoumer crater is actually quite significantly larger than that quite famous meteorite crater in the United States. Let's pop over to Australia, to my own patch of the world. And up here there's a hard one to find. Here it is. This one is about 900 meters across, so again smaller. The Tenoumer crater is more than twice as big, so we're looking at something more like this. Now that's the Wolfe Creek crater in Australia. Okay, so let me just get this up. So this is Australia, and what we're looking at is reduced to pole magnetics. So meteorites are magnetic, right? And we'll be talking about that in a minute with the Chinguetti meteorite. But also the craters that they produce can sometimes have a magnetic signature. And there's something interesting in this data, and you can see it as I zoom in here, this beautifully round structure. Now this is the reduced to pole magnetics. If I go back to the algorithm and turn on analytical signal, so we're now computing the square root of the sum of the squares of the first derivatives in the x, y, and z derivatives, x, y, and z directions. We're doing this in real time. This is not a current feature of ProRaster Scientific, but it will be in a future version, version 4.1, real-time filtering of data sets of unlimited size. So as an analytic signal, this thing just sticks out like dog's balls in the middle of nowhere, and I can tell you that this is genuinely the middle of nowhere. There's nothing out there. It's the Gibson Desert. There's just simply nothing there at all. There's no expression in terms of the terrain data. So let me turn on terrain, and you can see that there's just sand dunes and some hills, but really nothing to indicate any kind of crater there from the terrain data. And yet from this magnetic data, there's this really perfect circle, which is about 13 kilometers across. So that's just a little diversion. I discovered that the other day, and I just thought it was interesting. So coming back to Mauritania now, I want to talk about the Chinguetti meteorite. So here we are back in the vicinity of the Richat Structure, and down here on the edge of the sand dunes there's a little town called Chinguetti. And back in 1916 there was this dude called Gaston Ripart, and he was stationed in this little town, and he was told by locals of a meteorite called the Iron of God. and he asked if they could take him out to visit it, and they did. And he later described the discovery of this meteorite. He said it was 100 meters long, 40 meters high, in other words, the size of a decent-sized hill, which seems extremely unbelievable. But he did bring back a sample, which just happens to be a very rare kind of meteorite called mesosiderite. And so the guy's story has some kind of credibility because he actually brought back a sample of the thing. And so people have been looking for this meteorite ever since. So the way he described it is that it was about 45 kilometers southwest of Chinguetti, and it was to the west of a waterhole. So if we bring out our distance tool and we go from Chinguetti and draw a line 45 kilometers, well, at this scale, we're only getting out to about a range of 30 kilometers before we go off of the map. So 45 kilometers is quite a long way. In fact, 45 kilometers is about the distance from Chinguetti to the little meteorite crater that we saw before. 45 is right down here. So it potentially to the southwest, you're in this sort of breakaway country where there are hills, but certainly no one has ever found anything like the meteorite that he described. Also, in terms of, he said it was near a watering hole. Well, the only watering hole, or the only oasis around, is actually to the southwest of Chinguetti. And there's a little oasis in here, but it's only about 10 kilometres away. He also said that he got there overnight on a camel. Now, camels only walk at about 4 kilometres an hour. So I really struggle to think that he got anywhere near 45 kilometres away from Chinguetti. He was probably much closer than that. Anyway, people have looked for this meteorite ever since, and they haven't found any evidence of it whatsoever. And then there's a guy called Robert Warren who started looking for this in 2018 or something. And he did a pretty exhaustive search. There have been other expeditions. You'll find them on YouTube. There's a video about one. And so far, nobody's come up with anything. There was also an aeromagnetic survey flown in, it was either in 2005 or prior to that. So it was flown by Fugro. So this is in the modern era, so it would be a high quality survey. It was flown on lines 500 meters apart and 100 meters above the deck. So I haven't seen that data. It's not generally available, but apparently this guy, Robert Warren, did manage to acquire the data, and he looked through it meticulously and couldn't find any evidence of the meteorite. So meteorites, of course, are magnetic, and they're highly magnetic. And with these particular kinds of meteorites, the mesositerites, there are two kinds of magnetism involved primarily. So you've got induced magnetism and then you've got remnant magnetism. So induced magnetism is in the direction of the magnetic field. So if you fly a magnetometer over the top of one of these meteorites, assuming it was the size that Ripart described, 100 meters by 40 meters high, then it would generate a big positive anomaly, depending on whether you're at the poles or the equator, etc. And it would be very visible. When you add remnant magnetism into that equation, things can change. So remnant magnetism is a magnetic direction that's locked into the rock, and it can be pointed in any direction. It can point in the opposite direction to the induced magnetism. And this is a bit like having waves from different directions going over each other. So if the crests align, then the wave is higher. If the crests are out of phase, then you can get nothing at all. And it's a bit the same way with magnetism. So your remnant magnetism, if it's in the opposite direction of the induced magnetic field, can, to a certain extent, or perhaps completely, cancel out the magnetic anomaly or make it more complicated or more difficult to recognize. So there's a bunch of factors in there. The other thing I'd say is that clearly he exaggerated the size of the meteorite. Nobody believes that it can be that big. It's probably 10 times larger than what the actual meteorite is. So if you say that the meteorite is really only the size of a bus, then what are the chances that you've flown over it with an aeromagnetic survey on lines that are 500 meters apart? I would say pretty poor. This bloke, Robert Warren, was of the view that that survey extinguishes the possibility of this meteorite being out there. I don't agree. I think there's every chance, given the fact that it's likely to be 10 times smaller than the way that Ripart described it, that it's likely to have a complex magnetic signature which may actually cancel itself out rather than reinforce itself, and B, that you've got lines that are quite far apart, you're quite high up in the air, these things are on the surface, and so the magnetic signature attenuates very quickly. So all those factors, plus you've got the magnetic signature of the bedrock. Now, I don't know what that is, but if that's complicated, then it's going to make it much harder to find a tiny anomaly associated with a meteorite. So just my thoughts on that is that that survey does not extinguish the possibility that this meteorite exists. And poking around in the topographic data, you can find something which I think is interesting. So let's go back to our terrain. And out here, so Chinguetti's up here, and out here to the southeast. And it's interesting that he changed his story. Earlier he said it was to the southwest. Later he changed his story and said it was to the southeast. Out here, if you go past these dune fields, you can just see something in here which looks like a circle. And this could be the eroded remnants, topographic remnants of a meteorite impact crater. And what I have, I think I have another algorithm that displays this. So here we go, Chinguetti Crater. So let me zoom in. So using another feature here, real-time filtering, I'm going to do a low pass. Let me just turn these off for the time being. And I'll just change that view in a minute. Turn off that Butterworth, bring that up. So we're looking over here. You can start to see this feature, this round feature. So zoom right in, come back to my algorithm, and turn on the Butterworth filter. So we're applying a Butterworth filter in the wave number domain, in frequency domain. So what's happening is we're doing fast Fourier transform of our terrain data. We're processing it in the frequency domain, then reverting back to the space domain. And now I think you can see that feature more clearly. You can also see that there's sand dunes have gone over this northwest portion of the feature, so partially covered it up. The size of it, it's about 4.2 kilometers across. So I just bring that up as a possibility that maybe there is more evidence of impact craters in this area. And, you know, given that I don't think that the aeromagnetic survey that was conducted in 2005 exhausts the possibility of this meteorite being out there, I think there's more reason to keep looking.